Now, what we've done with our circuit, our example circuit here with bilateral symmetry, is we've considered two situations. One where, three situations, I guess. One where we put sources of equal magnitude and phase on either side. We had an odd mode circuit, analyzed that. One where we had equal magnitude but opposite phase on either side, so we had an odd mode circuit, and we analyzed that. And then finally, this last example, when we were doing transmittance parameters, we had a source on one side, non-zero, and a zero-valued source on the other, and able to go through and use superposition to analyze that circuit. But what about the most general case? What if we have a source on one side, an ideal voltage source, and a dissimilar ideal voltage source on the other? In this case, VG1 and VG2 are not at all related to each other. They don't have the same magnitude. They are not in phase or 180 degrees out of phase. Neither one is equal to zero. Can we still use the concept of odd-even mode analysis to analyze this circuit, this two-port device, where the two-port device itself has a plane of bilateral symmetry, where that symmetry has been destroyed by connecting two dissimilar sources to each of these two ports? It turns out there is a way to go through and use, and actually a very simple way, a way that essentially unifies all the examples we've done this far. So let's take our two sources, our two arbitrary sources on either side, and take the average of the two, VG1 plus VG2 divided by 2. Now these are complex numbers. We're going to add them together and divide by 2, and we're going to get a complex value. And this is what we're going to call our even mode source. On the other hand, we can go through and take the difference between the two source voltages, complex values, and divide by 2. And this we're going to call the odd mode source. Now, based on these definitions, we can go back and recast each of the two original sources, VG1 and VG2. We can rewrite them as simply, in the case of VG1, the sum of the even mode voltage and the odd mode voltage. And in the case of VG2, we can write it as the difference between the two. And you can show algebraically, go through and insert this into here and this into here and do the algebra, and you can see it'll work out. VG2s will cancel, will subtract out, and you'll get VG1. Or in the case of this one, if you insert these two and do the math, and the VG1s will subtract to 0, and you'll be left with simply VG2. So when you think about this is the average, and then this is sort of a delta between the difference between the two values. And so what we're doing is essentially writing VG1 as being the average plus the delta, and VG2 as the average minus the delta. Now this delta could actually be positive or negative, and it's complex, so again it's not really even defined as positive or negative here, but you can kind of think of it again as this way, as sort of an average plus or minus the delta. And so we can go through and our source on the left, we call VG1, we can rewrite as the sum of two sources, the even mode source and the odd mode source. The source on the right we can write as the sum of two sources likewise, the even mode source and the opposite of the odd, the minus odd mode source. And again, these two together are going to equal this, and these two together are equal to this. And again, this is a more general way of expressing, well, the examples we've done prior. In the case where VG1 and VG2 are equal to each other, what we'd find is the odd mode voltage would be equal to 0. In the case where VG1 and VG2 were equal but opposite, had opposite phase of 180 degrees, we'd find that the even mode was 0 and the odd mode was non-zero. In the case where VG1 was non-zero and the voltage VG2 was 0, we would find the even mode and odd mode voltages to be equal to each other, VG over 2 in this case. And so this general way that we've expressed here will comprehend the other three examples that we've done thus far. So this is really the way how you want to think about expressing your sources if you want to apply dissimilar sources to a two-port network that has a plane of bilateral symmetry. So now we just apply superposition. The first step is to turn off the odd mode sources, and we just have the same even mode source to the other side. Now we have preserved even symmetry within our circuit, and this planar reflection symmetry becomes a virtual open, and we can analyze the half circuit and find different values on one side, which then are equal to the corresponding values on the other. And I just gave 3 examples here of currents and voltages that we can find. So this is what we've done before. In the first example, this was VG over 2, and this was VG over 2 for the even mode analysis. I'm sorry, in the first example, these were the same values. In the case of the admittance matrix, this was VG over 2, and this was VG over 2 as well. Again, for more general sources, just calculate the even mode voltage and place that value there, whether it's 6 or minus 23 or either 4 times either j pi over 2, whatever it is, whatever it is, you place it there and do the analysis. So to complete the superposition, we turn off the even mode sources, and again, by turning off, we're setting the voltage equal to 0, making them a short circuit, and we turn back on our odd mode sources, the odd mode voltage of over here on the left, and the same odd mode voltage only multiplied by -1 over here on the right. All right, so same magnitudes, but out of phase by 180 degrees. Now, because of the symmetry of the two-port device, our plane of reflection symmetry becomes a virtual short, and we can go through and determine these values by analyzing simply the half circuit, knowing that this is effectively a short circuit wire, effectively, if you want to think of it, that runs through here with no reactance or of any kind, inductance or capacitance, just a structure where the voltage difference must be 0 at between any 2 points on that plane. So we analyze the half circuit, we find one side, and we can use those answers to determine the answers on the other side. But in this case, of course, we have to multiply those answers by a -1 by either j pi. We have to shift its phase by 180 degrees. So the completion of our superposition is we turn both sources on even and odd mode, which brings us back to original source voltage VG1 and VG2, and then we go through and we add the odd and even mode solutions for the different currents and voltages. I1 again would be I1 even plus I1 odd and so forth here. On the other side, you take I2 even and I2 odd, but remember I2 even is equal to I1 even, but I2 odd is equal to the opposite of I1 odd. So again, this sign problem can kind of cause issues for students. If you determine the even and odd mode voltage for the left side here, you add them together to find the total, but you take those same two values for the left side and take the difference to determine those corresponding currents on the right. Again, what we find is if these two voltages here and here are dissimilar, we have destroyed our symmetry, so there's no way there's no argument, and in fact it would be incorrect to argue that I1 is going to be equal to I2. That I1 and that I2 are not going to be equal to each other. This is the sum of the two even and odd mode solutions for the right side. This is the difference between the two. So they're going to be different values. I3 is going to be different than I4. Even though they are related by the plane of symmetry, we have destroyed that symmetry by dissimilar sources, and therefore these two currents will not be equal to each other. Again, this will be the sum of the even and odd mode solution for the right side. This I4 will be the difference between the even and odd mode solution from that right side. So make sure you get that straight in your mind. So the even and odd mode sources that we showed here, demonstrated, have all been ideal voltage sources. What about current sources? Let's say we're trying to go through and do a circuit analysis to determine, let's say, the transimpedance parameters of some two-port device. We'd want to apply ideal circuit current sources, rather, to go through and do that analysis to find the open circuit voltage. Could we use the idea of odd even mode analysis if we had a two-port device that exhibited bilateral symmetry to do that, where we use current sources? And of course we we could. It's the same equation, same math rather than what we did earlier. The even mode current source is simply the average of the two. We take the current source on the right and left, they're dissimilar, and take the average to find the even mode, and then take the delta, the difference between the two, and divide by 2 to find the odd. Again, IG1, the source on the left, then is simply the average of the two plus the delta. For IG2 on the right, it's the average of the two minus the delta. And so, again, you can show that these two things are related algebraically. Insert these results here and here to show that these equations are correct. Now, there's one catch, though, in how you implement even and odd mode current sources. You need to be very careful. This is an issue that students oftentimes frequently have errors associated. So be careful and pay attention now to this next slide. The key thing when you're adding current sources to remember is you don't add them in series, you add them in parallel. And so if I have a current source on the left side, IG1, and I want to replace it as a superposition of the even and odd mode current source, we would write these two current sources in parallel with each other. Makes no sense to put two ideal current sources in series with each other. They would simply confuse it. What if I take a current source that says I must be equal to 1 and put it in series with a current source that says I must be equal to 2? Well, you've got a problem there because the two current sources, ideal current sources, are trying to enforce a same constraint, a different constraint for the same value of current there. But it will work if you put them in parallel. And clearly from KCL, we see that the current coming out here is the sum of the even mode current and the odd mode current. They add together, and that becomes the current IG1. Likewise for the other side, the right side current source, that is the difference between the even mode current and the odd mode current. And again, by KCL, we see IG1 is the difference between this minus the odd mode current, or this plus the negative of the odd mode current. So make sure that you put your current sources in parallel when you apply even and odd mode sources, and likewise for voltage sources, there you put your sources even and odd in series with each other. I alluded before that perhaps you've seen a similar concept in your circuit analysis. In microwave engineering and sort of passive linear circuit engineering, we talk about this symmetry analysis as being odd mode and even mode analysis. In electronics, we have a similar concept, actually the exact same concept, but there it is generally spoke of with respect to common modes, which is the even mode, and differential mode, which is effectively the odd mode. And it is most prevalent when we go through and analyze differential amplifiers, differential pairs. Again, we have a plane of bilateral symmetry through the two-port device, the two-port being the differential amplifier. Most of the time we have different voltages on port 1 and port 2, but we can go through and define them as common mode sources, even mode sources, and differential mode sources, and go through and do an analysis where one you have a for the differential mode you have a plane, a virtual short rather between them, and for an odd mode or even mode, common mode analysis, you have a plane which is a virtual open. And so we can split the circuit into two pieces and evaluate each half circuit to get the answer and reflect the answer to once for one side onto the other half circuit. So it's exactly the same type of procedure that what you've probably done before in your electronics class.